So before I change the slide, let me ask this question. Particularly if those of you are California-based, how many people here have actually heard of ZocDoc? Understanding our application here requires at least having a somewhat high-level understanding of what we are as a company. So, all right, let me ask another question. How many people here have ever tried to get like a same-day or a next-day doctor appointment and failed? Okay, that's more relevant to most people. So that's the problem that we're trying to solve. Basically, there's a huge efficiency gap in healthcare access today. There are public studies that show that across various markets in the United States and across different specialties, the average wait time for a patient is 24 days to get an appointment. So that's clearly not at all helpful if something hurts today. On the other hand, from the doctor's point of view, and this is something that we've calculated from public research sources as well as our own experience working with our clients, close to 30% of appointment times go unfulfilled. And this is often resulting in like last minute cancellation. So you have patients who can't find a doctor or get access to a doctor, and doctors who can't manage their inventory very well. So again, huge efficiency gap, and that's where ZocDoc comes into play. So we're a technology company, we're an app or a website that creates a marketplace for patients and doctors. In particular, doctors go up and tell us when they're available. It's kind of like an open table type system. Patients can go and find a doctor and book an appointment. And ultimately, our talk today is going to talk about insurance. But before we get into that, I'm going to just give a little kind of static demo of what we do. So generally, most, at least new patients, will come in. They'll type in our search engine what is wrong with them or what kind of doctor they think they need. They get to a search results page. They can see all these time grids, and they say, okay, well, here's a doctor. I'm going to click on one of these. And then they get to the doctor's profile page where they can read reviews. And one of the most important things that we do, as opposed to, on top of just the booking availability, or booking application and the ability to screen doctors by reviews, is to actually find an in-network doctor. Has anybody here tried to find an in-network doctor using their insurance company's website? How was that experience? Yeah. They've at least given you the ability to sort alphabetically, which is, like a major milestone in their innovation ladder. So that is probably one of our biggest value adds is that alone, finding an in-network doctor with a somewhat modern and clean interface. And, we found via numerous experiments and user research studies that when patients have some degree of comfort or security that the doctor is in network, they're much more likely to go to the doctor, right? So ZocDoc's actually been around for 10 years. When I tell people here in San Francisco about it, they're like, oh, yeah, that's an amazingly new startup idea. We're actually kind of an old idea at this stage, but it's a very localized marketplace. So you can dominate in one city and be relatively unknown or have low penetration in another city. But if you like the sound of it, we are in San Francisco. We're in the Bay Area. Start using it, and then it'll get bigger, right? These things grow via network effects. But as you can see, the average wait time on ZocDoc for an appointment is 24 hours. So we've gone from the typical US patient, which is 24 days, down to a order of magnitude unit difference of 24 hours. And that's amazing. Now going to the doctor can be as fast as like urgent care. We could keep people out of emergency rooms, et cetera. But again, I'm not here to necessarily sell the company. Ultimately, we're a marketplace. We're trying to bring and connect patients with doctors. One of the biggest friction points for the patients is insurance, right? And again, I've already mentioned, this is one of our strongest value adds. And, just to get a sense of why insurance is complicated, here's just a quick collection of insurance cards. This is sort of, this is the thing we keep in our wallet that contains all the information we'll ever need to know to be able to have someone else pay for our healthcare. But parsing it is difficult. We've done surveys. 35% of the average American has difficulty reading their card, right? There's multiple dimensions on there. One of the challenges, there's no standard format. Like the insurance giants haven't been able to get together and said, like, let's just templatize this. And worse than the 35%, when you get to younger people, 44% of millennials find it difficult. So that's, and ZocDoc, not surprisingly, over-indexes towards younger people. So nearly half of our user base can't figure out their insurance card. So as we haven't introduced her. I'm Brian, Director of Data Science, and this is my colleague, Chris Smith, Senior Principal Engineer. We're a very product-oriented company, so our product managers go and design managers go, and they've identified this as a particular problem. And so we want to streamline the search experience. We want to streamline the process of finding a doctor. And the insurance card, we something that we had already been doing was capturing people's insurance cards and just acting as a pass-through, giving them to the doctor. So when you book an appointment, the doctor just gets a file of your insurance card. That way that, they could manually verify like your in-network status and your eligibility and things like that. We thought, maybe we can do this ourselves, right? Maybe we can automate this workflow. And despite the fact that insurance cards have a lot of information on it, you only need a few key pieces of information to be able to, for instance, verify eligibility. And that's, your name, your insurance plan, your member ID. But when you look at the card, you're like, okay, well, which one is the member? There's 8 different numbers on here, with like descriptions that aren't necessarily standardized words and things like that. So clearly some complexity there. And our vision was to just create some sort of magic function where you give me a card and then I can automatically parse the key relevant information. That information then can be used in various other APIs to, again, verify eligibility. So we had this grand design. We just needed to solve for this magic box. Naturally, neural networks can solve all problems. So that was a clear first place to start. And we got humbled pretty quickly. One can just throw a neural network at the problem, but one can get abysmal accuracy if you just sort of start very naively. And a big part of the issue we found is that while the sort of setting up a neural network and building a neural net is very easy and straightforward, our problem suffered from a lot of pathologies, right? We're doing classification on a dimensionality of like the insurance plan, which is on the order of magnitude of 10,000. The images that we're dealing with are very dirty, very, like everybody there's different issues in everybody, taking a photograph on their phone. So we had to solve for these things. And it took, the majority of what we're here to talk about today is that, after we set about to do this, we were able to build a prototype relatively quickly, and a good stable prototype that was good enough to deploy. But this was our first deep learning and neural net application. And so what we're trying to do here in our story is share some of the wisdom that we went through. So if you've been deploying deep learning models for 5 years at this stage, maybe this can just be a refreshment of older times. But for a lot of people who are not necessarily deep learning experts, but coming in as engineers or data scientists, wanting to build these applications. Because again, the prototypes are very easy at this stage because of the prevalence of good open source software and pre-trained models and everything. But bringing, the core challenge that we ultimately faced was after the prototype, reproducing that prototype, making it as reliable and as robust as all of our other engineering infrastructure. So I'm going to hand it over to Chris, who's going to give the sort of timeline and discuss how we started with the prototype, how we improved it, and what did we learn to get to that place where we could actually reproduce this thing.
Oh, good one.
Oh, wait.
Seem to have lost my clicker. All right, cool. Yep. Sorry about that. Let's just bring the slides back. All right, great. Hi, everyone. My name's Chris Smith. I'm a principal engineer at Zocdo, and I was the lead technical person on this project. So I was responsible for both designing the initial prototypes of our model, bringing those into production, and then maintaining them over time. And I'd like to tell you a little bit about the history of how this project evolved and some of the complications that we faced along the way in reproducing our models. And hopefully you'll be able to take these lessons and apply them at your own work and not have to go through the same pain points that we did. So with that, let's talk about how we got started. So the first thing that we needed to do was just collect the data necessary to train these models. As Brian mentioned, we had the insurance cards already in one place in our system, and we had some of the insurance data in another place, and we had the member IDs over in another place. So we kind of had to perform some ETL and bring all of these separate data sources together into a central location. And we chose S3 for this. So we just extracted this data and dropped it into S3. However, these data sets were not able to be directly linked, so we had to use some heuristics in order to match these sources together. And this was OK to begin with. It was enough to get us started for our model training. So after we had the data in place, we need to set up some infrastructure so that we could actually train the models. So we're purely in Amazon. So we set up some EC2 instances on the P3 instance type. And we used a bunch of EBS volumes to actually store the data locally. And this is a very natural fit for us because we're already familiar with these technologies. So we didn't have to learn a whole new system and introduce additional complexity at this stage where we weren't even sure if we were going to be able to accomplish our goals yet. The software side of things, we brought in Keras with a TensorFlow backend. We chose Keras because of its really low learning curve compared to other more research-oriented frameworks. So myself, I'm a software engineer. I don't have the deep learning background from the research side, but coming into Keras, it was very easy to figure out how to train a neural network in order to perform the tasks that we wanted to do. And if we needed to dive deeper, we could always jump back into TensorFlow, which was really nice. And we did most of our research within Jupyter Notebooks because they gave us this fast iterative feedback cycle where we could work directly within them, figure out what types of results we were getting from our model, analyze some of the pain points, look at the metrics, and then take those ideas and create another model that we think would address some of these pain points. Now, this fast iterative feedback loop was really important for us early on because we needed to prove to stakeholders that this technology actually worked and is something that we could bring into our production environment to solve real problems. We started this, I think, at the beginning of 2017, which was like the beginning of a really substantial AI hype train. So we wanted to prove that AI was more than just hype to the organization who had little familiarity with it at that point. And the iteration process was key here, right? Because we were able to prototype a model, get some results, take the ideas, create another model, get better results. So this accuracy on the right is for extracting the member ID. So going from image to the actual text of the member ID. I don't have time to talk about all of these iterations right now, but the important point here is that we got our prototype to near human level accuracy. So the human level accuracy we measured at the beginning of the project from the existing data sources that we already had. And we saw that most humans, when they would get the member ID wrong, the things that they would do are either select the wrong ID on the card, so they would type in the wrong numerical digits, or they would make like single digit typos, and they would swap characters and those types of things. So once we were at this human level accuracy, we decided to take this into production. Technology. So we took it into production, and we launched this back in October. And this is kind of what the flow looks like from the user's perspective. So instead of scrolling through this giant list of insurances on our website, you can instead take a photo of your insurance card. We'll then present you with the most accurate, or what we think is the most accurate insurance carrier and plan combination, which you then can change if you think we got it wrong, which allows us to create a feedback loop to improve our model. And then later on, once you've found the doctor that you want to book and you've selected a time and you're in our checkout process, we'll have the member ID there, and we've also used that information now to make an enhanced eligibility check against your insurance carrier to verify that your coverage is still active and tell you what you can expect to pay as your copay. And the reason that this is like several screens later is because it also requires you to select the doctor, because that amount is going to be different depending on the doctor's network status with your insurance company. So after months of hard work, we took our much-needed vacations, got some rest and relaxation, and we came back to this problem with fresh eyes, and we started thinking about things like, how do we retrain the model? So we have this thing in production, but can we improve it? Can one of our teammates reproduce the results that we released? Essentially, it came time to pay our debts. So we had accumulated this debt, creating the first prototype of the model, and we had to pay down this debt now so we could plan for the long-term maintenance of this product. So let's talk about some of the barriers that we hit trying to reproduce the results from our original model, and then some of the improvements that we made along the way. So for us, a reproducible model simply meant that we're able to take the same data that we had before, the same network architecture, and get about the same level of accuracy. So it wasn't important to us to get the exact same loss that we had before, just something in the ballpark so that it was comparable. And we found that we weren't able to do this, which was really worrying. And we started to look into why. So one of the first things that we noticed was that the way that we had handled our data or mishandled our data caused a bunch of problems. So I mentioned before that we dumped our data into S3, but we also had these local EBS volumes on our EC2 instances. So this required the engineers to copy the data down from S3 to their local EC2 instance, where they would then run a training experiment. And we had a bunch of these EC2 instances where you would be running multiple experiments with multiple different model types at the same time. So you might have one EC2 that has the latest copy of the data, but you might also have another EC2 that was updated yesterday, maybe one that was updated last week. And this created a huge problem from a reproducibility standpoint because we didn't know which data set the final model was trained on. We also had local artifacts where the training process would create things in order to optimize for training speed by creating things like thumbnails or some type of intermediate result, and it would just store those on the local volumes as well. These weren't reflected back in the source of truth, which was S3. And additionally, the data in S3 kept changing over time. So we kept getting new insurance cards, having new appointments booked on the site, and we were syncing these into S3, but we didn't know at which point in time the model was trained on a particular subset of data. So if we were to retrain a model, we might be using different data now than we were at the original training session. So in order to fix this, we moved into a streaming model where the data lives inside of S3. It's no longer copied down to the local hosts for permanent storage. It's just streamed in during the training phase. So before training even happens, there's an ETL phase now, which does any transformations that we need and stores this data permanently in S3. And then during the training phase, we're able to pull that data just when we need it, and we store any output artifacts like logs and metrics back into S3 so that they're accessible even if we turn these machines off and they go away. In order to solve the versioning problem, we created version datasets instead of just pulling whatever happened to be in S3 at the time. And set up predefined train test splits, kind of like you would deal with something like Kaggle, where they have a holdout set that you can't access. And you could explicitly version this. So we have an explicit version on the data set, so we know exactly which set of data we trained on. We know exactly who's in the train set, who's in the test set. And if we want to compare architecture changes now, we can train a model on the exact same data set that the previous model was trained on and know with confidence if this architecture is better than our previous architecture, and it's not just due to changes in the underlying data. Oh, man. The next pain point that we hit was the environment that we were training these models in. So because this was a long-lived project, right, several months of work, we had these EC2 instances that would drift in their configuration over time. So initially, we didn't know all of the software packages that we needed to install, and then TensorFlow kept releasing updates, Keras was releasing updates, and we always would try to, install an update and get some bug fixes, but we would forget to update all of the other machines. So what would happen is an engineer would go train on one of these older EC2 instances. They would either get very different results from a prior version, or they would hit some bugs in the middle of training, which just wasted everyone's time. In order to fix this, we moved all of our software dependencies into Docker. So Docker images are great in that they allow you to package everything kind of like a virtual environment, but like better because they capture everything, including the C dependencies. You can then store that image inside of a container registry like ECR. And then when you're training, you can pull that image down to the EC2 instance and have an identical environment as the one that's on the next EC2 and the next EC2. And because these images are also versioned, they're not going to change over time. An interesting thing that we did here was that we only put the software dependencies inside of the Docker image. We didn't place the code that we're using for training, just volume mounts, which allow you to share files from the host operating system into the running container, which improves the iteration and feedback process for our engineers because they don't have to create a new Docker image and push it into ECR and then pull it down in order to train. So the third thing that we ran into was how we were managing our code. So initially, we had done most of our training within Jupyter Notebooks. And I don't think that's going to play. OK. So we had done most of our training within Jupyter Notebooks. And you would go through this process of like editing a cell, running it, get some results, not liking what you saw, changing the code, editing it, running it, get some results. And this process of editing the notebook over time and not necessarily running it from top to bottom every single time harmed our ability to get reproducible results. So Joel gave a really great talk about this at JupyterCon, which you can check out if you want some more details. So the short of it, though, was that we think Jupyter Notebooks are great for quick iteration and learning, but not necessarily so great for getting reproducible models. Because of these ordering guarantees, you have to be pretty strict with your processes in order to get reproducible results from them. So we moved from notebooks to scripts, both Bash and Python, in order to do our training now. So these scripts take in all of the parameters, all the hyperparameters that we use to train our models, including things like which weights we're initializing from and what the name of the experiment is. And we check these into source control. So within our Git history now, we can see that, oh, we're running this experiment, and this is why we thought this particular change was going to improve our results, and we can go check out that exact version of the code, run it, and get the exact same results, which is really nice. However, reproduction of the original model that we had in production was still elusive. We could not reproduce the results that we had already deployed, and this was a problem, but we made the hard decision to give up on reproducing this original model. We weren't giving up on reproduction entirely, just of the thing that we already had in production. What we wanted to do instead was focus on creating a new model that was not only reproducible, but also better than what we had already released. And in order to do that, we need to understand where our current model was failing. So because we had rushed through the initial dataset creation process, we didn't really spend much time exploring our dataset. So we returned to that as our first improvement. And the things that we were looking for by examining our dataset again were things like class imbalance, bias, bad labels, and leakage between the train and validation sets. And basically, we found examples of all of this within our dataset. And we attempted to fix them where we could. So we had some extreme class imbalance. This is a log scale plot of all of the insurance carriers that we're training on. And for the most popular insurance carriers, we have something like 10,000 times more training samples than we do for the least popular carriers. So we tried oversampling here in order to improve the accuracy on these underrepresented carriers. In practice, though, this wasn't a huge issue for us because this scale, or this distribution, also reflects the volume at which the appointments are booked on our site. We also had a class imbalance in the rotation of insurance cards. So some photos would be in a perfect landscape position, but others, they would either be rotated 90, 180, or 270 degrees. And the image itself is not necessarily rotated all of the time, just the card within the image. So you might have a landscape image with a portrait insurance card. We also had examples of bad labels in our data set where the humans were confused because they labeled the ground truth as the number on the right in one instance, but the number on the left in another instance. And if these balances were about 50-50, the neural network wouldn't be able to determine which one was the correct ground truth, so it would just kind of pick something in the middle in order to minimize its loss. In order to solve this problem, we actually trained a model to detect some of these bad labels. So we were able to go ahead and clean up our data set and improve it that way. And that made a huge difference in terms of accuracy. So I would highly recommend giving your data set a checkup. We also labeled a new smaller data set that was not created through this fuzzy matching process that I talked about earlier. And we found that our initial model was about 10% worse on this newly labeled data set than it was on our original data set. And we've worked on closing this gap ever since then. So after we've examined our data set and we understand that better now, let's talk about some of the improvements that we made to our model itself. So this is our original model, and it's 3 stages. The first stage takes the image of the insurance card, runs it through a VGG16 classifier with categorical outputs for the carrier and plan labels. The member ID is a bounding box with 8 points on it, so the XY pairs for all 4 corners. That bounding box is not very accurate, so we send it through an attention and alignment model. This is a transformer model, which would then output a better version of the bounding box, which we would then feed into a recurrent neural net in order to do the OCR. Our first hypothesis on why the model was not performing as well as we thought it could was just because we were wasting pixels. So the input to the VGG, I think we had set at 256 by 256. But if the insurance card is not taking up all of the pixel space in the original image, we would resize it, and then we would waste about 40% of the pixels. So what we wanted to do was crop this image to just the insurance card before we fed it into the first network. However, we didn't have labels for this data. So we had to generate a bunch of data in order to do this, right? We needed to generate card bounding boxes. So we had Photoshop, though. So we took insurance cards, Photoshopped out the background. We now have a transparent image, which is just the insurance card. We can then overlay that on top of another data set for the background, and we have perfect data, right? So we can train a network now in order to do this. So we trained, we trained a SSD model to predict the bounding box of the insurance cards. So SSD is a single forward pass model that predicts multiple bounding boxes. We did have some images which had more than one insurance card in them, so that was important to us. But for the most part, we just have a single card, we got a box, and then we can crop the original image to just the insurance card. The next thing that we wanted to improve was the bounding box that we were predicting for the member ID. So our hypothesis was that the dense layers in between VGG and the bounding box output was harming its results. What we would see ideally is a perfectly aligned bounding box as the output, but in reality, we would see like 10 pixel off predictions. And we thought this was the case because of how our loss function was working and how the dense layers allow the output to not be directly tied to the pixel space in the input of the convolutional windows. So in some cases, we would even get a box that had one of its axes flipped, which would then produce a garbage output like this, where the member ID is rotated. So what we wanted was pixel level accuracy for the member ID predictions, because even a small pixel loss will cut off a whole bunch of text, which is going to harm our OCR model. So we used UNet to do this, and we had UNet trained to predict a output mask for the member ID, and we also had to predict another mask just for the text. So by having it predict both the text and the member ID, it was able to train better. So this is like a 2% increase in accuracy as opposed to just training the member ID output alone. So once we took the cropped insurance card image and fed that into the UNet model, we would also have it output a rotation classification. And we would use the two of these to generate just the text of the member ID. So this is still an image at this point. And we took a look at the final stage and how we were doing our training. So there were a bunch of issues that we found within our training. I don't have time to talk about all of them today, but I will touch on some of the augmentation and issues with our loss functions. So in order to read the member ID, we use an algorithm called CTC, which is a loss function for training recurrent neural nets to do sequence-to-sequence predictions. So the image here is fed into the recurrent neural net one column at a time. So each column is a time step. And then in your output, you have one output for every input, but the activations on the Y scale are the letters. And you can have them together in CTC loss. And that's OK for its like interpretation. So what I mean by that is like you'll see that they're kind of wide sometimes, and CTC can interpret that as still one letter because they're next to each other, and it doesn't have a space in between it, which is what's on the bottom. So when I say that we're using our loss functions incorrectly, though, we weren't taking advantage of the fact that CTC can handle sequences of different lengths. So it can handle the input and the output sequences at different lengths. But what we were doing is just rescaling the original input into a fixed 64 by 512 image. So sometimes we would stretch out the member IDs if the member ID had more characters in it, and other times we would squish the member IDs. And what this would do to our network, if you look at the activations here, you'll see that we have some confusion in yellow where it's not sure if that's an 8 or an R. And at the 1 and the 3, it thinks that there might be a break between them. So we end up getting duplicate outputs when we decode this. So we get 1133 instead of just 13. In order to fix this, it's pretty simple. We just modified our training process to use our loss function correctly and fed it a variable length input. So whereas previously we were scaling this image before we were feeding it in, now we keep the height fixed and the length is variable. So you'll see that the activations look much better here. And if you look at this on different sequence lengths, it looks something like this. The network has learned to predict correct strong activations regardless of the sequence length now. So our prototype at launch, if you remember, was around 80% accurate. Once we made all of these improvements to our training process, we finalized our data set. We're able to, oh my goodness. We're able to improve the accuracy by our model by almost 13% absolute, which is quite a substantial improvement. And this model is now reproducible, which is really great. So in closing, reproduction can be difficult. I would encourage you not to spend efforts trying to reproduce the wrong thing. The things that you want to focus on are the code, the data, and the environment that you're training in first. And then after you get those, you can look at things in your training process and your loss functions. And this is critical for maintaining these neural nets over time. Thank you. And with that, I will take questions.
So we've got one mic. I'll walk around and.
Thank you. I was curious, after this experience, have you looked into, is there any kind of platform that does help you in terms of like versioning and, you know, or is it all kind of homebrew tools that you have to stitch together?
Yeah, great question. So as you know, we're in the healthcare space, so we have to abide by things like HIPAA regulations. So a lot of the services that were just starting to pop up around the early 2017 weren't available to us yet. But more recently, services like SageMaker have become HIPAA eligible. And one of the really nice things that service forces you to do is actually input your files in a versioned way. Like you have to provide paths into S3 for your training data. So there are services like that that kind of force you into that paradigm, but you do lose some of the flexibility when you're going to use a managed service like that.
Just follow up on that. Yeah. You mentioned the ETL process. Is that just hand-coded, stays outside of any type of versioning?
Well, the code that is the process is versioned. That's all checked into source control. So we use a couple different technologies there. Like we have an architecture that we use internally that's built on Lambda and some other pieces that use Spark. For this one, though, I think we just had a series of Python scripts that moved most of the data around. Yes, yeah, everything's in Git now, which is...
Hi, this was fascinating. One of the questions that I have is around the effort and the time horizon for this entire undertaking. How many people worked over how long, and how it played out over a timeline?
Yeah, there were, I think, two of us doing the research side of this, the actual neural net architecture. The team itself that supported the production service is a little bit larger. I think there's like 6 engineers on that team. The research phase, we had our initial prototype doing some classifications within a couple days, really, of getting the data in the right spot. And then I think it was probably like over the summer, so like 3 months to launch. And then since then, it's been another 6 months or so.
I mean, mostly it's been Chris working on it. So like, when he's got spare time. Any other questions?
Thanks for a great talk. It's really detailed and informative, which some talks might not be. But I'm curious, like this seems like a very specific use case and model. What are the plans for future models or other projects that the team is working on?
Yeah. Brian, do you want to take it?
So this is a very specific application, isolated use case. I mean, machine learning in general at Zocdo, a lot of it is focused on the search experience. Making sure that the results are relevant, getting towards a place where we could be personalized, the one kind of very broad statement is that within healthcare applications, machine learning and tends to be, or like a lot of the technology tends to be a few years behind what standard internet companies might be doing. So like where search is, I wouldn't call it a solved problem entirely, but like very well understood problem. Like there's aspects of, in particular, there's regulations that prohibited us from taking a very aggressive machine learning posture in previous years. And like we're slowly working through those and bringing about better data-driven techniques to the product. That's, I guess, I mean, we'll stick around and answer questions, but the official answer.
it was beautiful to see the journey from having the prototype to going all the way till the end. So one question is about when you started the prototype, you had to have data. What did you do to collect it? What did you do to, and how much of it did you get? And secondly, when you're talking about augmenting the data to generate so much,
Yep.
is there still any common tool people use, or is just everybody does it themselves?
So augmentation, there's a couple like frameworks that do it for you. So I have a couple libraries I could recommend. In terms of generating the data for like the card bounding boxes, that was something that we wrote. I would love to see tools come up in that area. Like I think 3D modeling, especially like using Unity, would be super interesting for a lot of problems. Yeah. Was there another part to the question? How much data? Yeah. So the total data set size was fairly large, like I think over 1 million cards, but we weren't able to use all of it for our training process. Our training process was probably down to like 40,000 or so. So still big.
And again, we had already released an application where they can submit a photo. We just didn't add any intelligence on top of it. So we had close to a year collected the human labeled images.
Yeah, it definitely helps to have a product that's collecting data first before you try to train.
All right, we'll stick around and answer questions, I guess, in the back or anything in the next 10 minutes. But, thank everybody for coming to our talk.